because she's show up yet.
Yeah.
Okay, but you can start.
So, good morning to all participants. Now we are starting the special session, Stochastic Processes. I would like to introduce the invited speakers of this session, Professor Paulo Oliveira, Professor Nicola Privou, Professor Benedita Ferrario, and Professor Anabela Cruzeiro, and thank all of them for accepting my invitation. I'm very glad to see all of you. It is a great honor to have you in this Portuguese meeting organized by SPM. I also thank very much the SPM's team for the organization of this fantastic conference. And I also thank the kind invitation to organize this special session. Our first speaker of this session is Professor Paulo Oliveira from the Department of Mathematics of the University of Coimbra. Presently, Professor Paulo Oliveira is Director of Faculty of Science and Technology of the University of Coimbra with many academic duties. Is true, Paulo?
No, I try to make the staff do all the work for me, so...
Yeah, you good idea. I thank him very much for your presence. Paulo Oliveira has a wide research work in the areas of stochastic process, probability theory, statistics, and statistical modeling. And today we'll talk about aging and probabilities of exceeding the mean. Please, the screen is yours.
Okay, thank you, Fernanda. Well, first of all, thank you for this for the invitation to present a talk. I would also like to thank to the speakers that due to a late commitment that follow from the what Fernanda just mentioned, I had to change a little bit the schedule. So thank you for helping solving this this late difficulty. I will now try to share the screen so you can actually see my slides. So as usual, it is now that the okay, now it should be working now. Now the browser is starting complaining that it would not allow, but I think I have convinced. So I hope you are seeing my first slide. And you are probably noticing that I had changed slightly the title of my talk, because instead of referring just to aging, I am also referring to skewness, because the reading of the concepts that we will be discussing can be seen as aging as they are in more reliability theory, if you are concerned with reliability theory, but if you are concerned with more geometric properties of the distribution, so you probably will be interested in looking at these things as some kind of measuring the skewness of the distribution. Well, this has been joint work with two colleagues from Coimbra, so Idir Arab, who is a postdoc in Coimbra, and Beatriz Santos, who is a starting PhD student. And this has also involved Milto Hadjikyriakou from Cyprus and Tilo Wiklund from Sweden, Uppsala in Sweden. Now, well, the framework. The framework is the following. So you are mainly concerned with non-negative random variables, although some of the things I will be discussing also can be applied to real random variables. And well, the notation is the usual. So you have distribution functions, density functions, and we'll be looking a lot at the behavior of the survival functions, so the tails of the distributions. Now, the main goal of this thing is to order distribution. So we'll be referring to order with respect to aging or to skewness. And the two concepts that I'll be, well, there are lots of stochastic orders available in the literature, but I will be concentrating on the convex transform order, which requires that this composition here is a convex function, or in a somewhat milder stochastic ordering, which is known as the star-shaped order, which is referred to with this small symbol over here, which requires that this same function as above but divided by x is increasing, or as it's also known in the literature, that the function c over here is, instead of convex, is star-shaped. Now, well, I will not go into details of course, of the mathematics of all this, but you should have some insight about what this means. So star-shaped, well, by the way, convex ordering has been introduced in the early 60s of the last centuries. It has remained, well, you find a few references on the literature, although surprisingly there are not that many explicit results about how to actually order given distribution. So you have general properties, but not really actual results that allow you to say something explicit about specific distributions. And star-shaped appeared later on the literature, and well, even fewer available explicit results in the literature. Now about geometric. Sorry?
Oh, I don't see your screen. I don't know.
I should be. Let me just see if. Sorry.
Maybe you stop it. Okay.
Is it?
No, it's okay.
Is it okay?
No.
Okay. Sorry. So I probably did something wrong.
Yeah.
So I was just saying that in order to get some geometric insight about star-shapedness, so you look at a function. So and the idea is that whenever you consider a ray starting from the origin, so a straight line, up to the intersection point, you should have the graphical representation of your function below the straight line, and this should happen to every straight line that you might consider starting from the origin, just to have some geometric insights about what star-shapedness mean. Now, the geometric insight is something which is well, actually really explored, because even convexity, we don't deal it with the traditional way, where well, everyone knows the definition of convexity, but we try to look at this in a more geometrical, with a more geometrical approach, in order to actually prove the results that you can try to tackle. And the idea is, you look at how do behavior the intersections between convex functions and straight lines. So if you make the difference between a convex function and a straight line, well, the sign pattern that you find will be also always plus minus plus. And it is simple to check that this is actually an equivalent characterization of convexity if you require that this is the sign pattern of the difference between your actual function and any given straight line that you might consider. So you will always find a pattern which is plus minus plus, and this has proved itself to be the best tool to get explicit results about the characterizations on the convex transform ordering. So instead of the usual definition of convexity, we will look at the convexity characterized by the difference between the function and any given straight line. We will have the sign pattern plus minus plus. Well, concerning star-shapedness, you can reason in an analogous way, and as you are only dealing with increasingness, it is easy to check that an equivalent characterization of star-shapedness is that this difference here has a sign pattern which is always at most minus plus. You might have so fewer sign changes, but if you have these are the most sign varying changes that you might find. Now, both the convex and the star-shaped orders are just partial orders, which means that not all distributions are comparable. It is easily seen that if you have a comparison in both directions, then actually you have just a change scale on the distribution. So if your distribution belongs to some parametric family where there is a scale parameter, you just can choose it as you please. Well, I'm mentioning here with respect to the convex transformation, the convex order, but this also applies to the star-shape order. Now, so in order to try to decide about convex ordering, so I remember here the sign pattern that characterizes the convexity. Of course, it is convenient to rewrite this with the explicit survival function. So we'll be looking at, well, characterize these things, this object here, so this difference for every possible choice of A and B, and check that the sign pattern that you find will always be plus minus plus, or minus plus if you are just interested on the star-shape order, and then you choose B equal to 0 because you don't allow well, time shifts on your representations. Well, of course, the usual problem is that the survival functions do not have closed analytical representations, so you have to well, find a workaround to try to say something explicit about your definitions. Now, well, this is just remembering the definitions. Now, in reliability theory, these orderings are considered as measures for aging rates. Well, the interpretation difference between these two is that if you look at star-shaped order, this means that you can only detect aging rates when systems have started working simultaneously, while the convex order allows you to detect things which, with respect to systems that have not started working simultaneously. If you prefer to have a more geometrical interpretation of this, both measures, both stochastic orders are considered as measures of skewness, with the restriction that the star-shaped order has the extra requirement that both distribution functions vanish at the origin. So you don't allow, again, shifts in your distributions. Now, as symmetric, as we are looking at at non-negative random variables, well, this is the picture that is taken as the symmetric position for non-negative distribution function, or rather density function, because I'm picturing here as a density function. And when you go smaller on the convex transform sense, or interpreting this is becoming less and less symmetric, this means that your density is starting to accumulate some mass somewhere shifting to the right. So, and as more it shifts to the right, it becomes less and less symmetric, or if you want, as I have written here, more asymmetric. So you go on with the convex transform ordering. Now, for the analytical treatment of this, well, it is, as we do not have closed expressions for the distribution functions, you rewrite these as integrals from something that depends on the density functions, which are usually explicit. And then you integrate on the tail, and the nice thing is that from the sign variation pattern of the function ht, as you are integrating from x to plus infinity and looking at this as a function of x, you can recover, well, up to some point, the sign pattern of the function v itself, which is the one that actually characterizes the stochastic ordering, and so you get the characterization like this. Actually, you can go a little bit further, but if you have some further analysis, so you can have a sign pattern for the function h, which is a little bit more complicated than just plus minus plus, but this requires an extra argument to end your results. Well, for the analytics, it is usually not convenient to look directly at the function 8, but you consider logs of both terms, as log is an increasing function, so the sign pattern does not change, and then you can do some mathematics on this. If you are interested just on the star-shaped order, you just take b equal to 0, and then you can proceed likewise. Okay, you just look for the sign patterns. Now, the two stochastic orders even have a link. Well, I did not mention, but it is easily seen that the convex transform order always implies the star-shaped transform order. Now, you have a comeback which makes it easy, because on the analysis of the sign patterns of these expressions, usually
please, sorry to disturb you, but maybe you have 3 minutes. You have no
3 minutes. Okay, I'll go fast into
Okay.
the results. Well, I also started a little bit late, so I can claim 4 minutes probably. So usually the difficult case is when you take B negative. So if you start with a star-shaped order and you prove it previously, then you can only consider B larger than 0. So this makes your life a lot simple. Now with all these tools, so this means that we can order lots of a few parametric families. Well, as described here in this slide, so you'll probably notice that surprisingly, all these results, although the definitions of the stochastic ordinals are relatively old, they were not available in the literature. How you do explicitly order these kind of distributions. Now, well, I'm mentioning results for the convex order, but even for star-shaped orders, you have relatively recent characterizations, explicit characterizations of what is happening. Now, well, I will skip the mention to parallel systems, which this is not well, as I do not have that much time. But I would like to refer about what is happening about the exceedance probabilities. Van Zvet already noticed that the behavior of this probability is monotone with respect to the convex transform order. Well, actually, this is basically a consequence of the Jensen inequality, but you can prove a sort of extended Jensen inequality that applies for this setting, which allows you to go a little bit further than just consider here the expectation. Actually, you can write this with respect to an appropriate transformation T, which allows you to take either the mean or the mode or the anti-mode if you are looking to compactly supported distributions, where the anti-mode becomes more interesting. Now you can prove these monotonicity results about the probabilities of exceeding the mean, or replacing the mean by the mode or the anti-mode. You will have analogous characterizations of your results. Now, of course, you can replace, or I just already mentioned, replacing the mean by the mode on the anti-mode, and you can have some explicit bounds for the probabilities of the mean, as showed here in this slide. Now, well, again, I will skip these results about parallel systems. And I will go into some results about negative results about compatibility with respect to the convex transform order. Now, it is simple to see that if you have a function which starts at 0 and approaches straight line, then this function cannot be neither convex nor concave, which means that if you apply this to our setting, means that you don't have comparability between the random variables that correspond to those given distributions. And this allows you to go well beyond the complex systems which have an heterogeneous structure on their components. And
sorry, but I think we already finished time.
I already exceeded my time. Okay, so if you allow me 2 slides more, I'll just end up with my talk, just to make explicit the difference between what is happening in the convex transform order. In the convex transform order, I was mentioning that if you have heterogeneous systems with one component which has a rate slightly smaller than all others in both sides, then well, you will have non-comparability between these two systems. So meaning that if you can decide which one is aging faster or which one is more symmetric. Now, if you want to go into more positive results, and now you have positive results with respect to the star-shaped ordering, well, there is an extended criteria that you have proved recently that allows to compare with respect to the star shape. Now, with using this characterization, you can have comparability with respect to the star shape order if your hazard rates well, here I'm mentioning Weibull distributions, but you have seen similar things with respect to the exponential distributions. If your hazard rates verify these inequalities over here. While I remember again that if you look at convex transform orders, then you don't have comparability. That means you cannot decide which one is more symmetric than the other. Now, of course, running out of time, so I will not go into further details, but this allows to be applied to a few other models where you can decide the star-shaped comparability when you don't have convex transform comparability. And well, the assumptions that we use are of this sort over here, and they are usually satisfied by the most common non-negative distributed random values. So thank you for your attention, and I'm sorry for exceeding a little bit the available time.
Okay, thank you very much for your nice talk. We have now time for questions, effectively. Then you can pass immediately to the second speaker of this section, Professor Nicolas Privot. Paulo, please, you can, stop. Okay.
I think I already stopped the sharing of my screen.
Okay. Thank you very much, Paulo.
So,
Professor Nicolas Privot is from the School of Physics and Mathematical Science, Nanyang Technological University in Singapore. Professor Nicolas Privot is specialist in stochastic process and its applications, namely in Levy-Jump process and its applications to mathematical finance. He is author of several very interesting books on stochastic process and its applications. And today, Professor Privot will speak about moments of Markovian growth collapse process. Please, Professor Nicolas.
Okay, thank you very much for the invitation. Can you see my slides?
Yes.
Yes, you can. So I can start now. Okay. Yes. So this talk is about growth collapse processes. I move to the next page. I suppose you can see page 2 now, which have been introduced a few years ago, and which are a particular case of those piecewise deterministic Markov processes, and which can be used in earth sciences, physics, and also recently in cryptocurrencies. So here in this talk, I will be interested in the computation of moments. We don't always see computation of moments beyond the mean and variance. It's not because higher moments are not interesting. It's often because higher moments are difficult or sometimes impossible to compute. So here I will look at the moments of those growth collapse processes, and I'm going to apply some techniques based on sums over partitions and things like this. Okay, next slide. So this is the idea of the growth collapse process. Maybe looking at the picture is the easiest way to understand how they work. As soon as you reach a certain level, such as here, you reach this level, and at this level, you may actually be at the time of a Poisson jump, because there's an underlying Poisson process in T with jump times TKs. And if you encounter a Poisson jump, then the process will collapse. That means it will be multiplied by the amount 1 minus UK, where UK is a random variable between 0 and 1, typically, a uniform random variable. So if you want, you can rewrite this as a differential equation. It looks a little bit like some kind of Einstein-Uhlenbeck differential equation. Anyway, it can be solved in a similar way. And there's an explicit solution for this growth collapse process. So again, I will be interested in the moments of this quantity. You can write the process through the explicit solution as a random sum, which itself can be written as a Poisson stochastic integral here. But the Poisson stochastic integral is somehow anticipating due to the presence of NT here. Okay, so now I'm going to review the literature. Okay, before that, yes. So those are the quantities I'm interested in. Okay, so I move to the next. Yes, so this paper is from a few years ago, Boxma and several authors. So what they do is that they compute the first moment, and that's a theorem. And what you can see here is not my own slide, it's not my own paper, it is just a screenshot of their paper. And you can see that computing the first moment is not very difficult, but not that simple as well, because they use some conditioning given the total number of jumps, and they do some computations. Anyway, I move to the next slide, because next slide they are computing the second moment. So again, this is not my work. This is just a copy and paste from their paper. Now, if you move to the second moment, it's much more complicated because it takes four pages, actually. So I'm not going to go through the detail. I just want to convince you. I don't want to make you confused, but the idea is I just want to show that it's a bit complicated. So page 1 from their paper, page 2 from their paper, page 3 from their paper, page 4, and then page 4, they reach this equation 49, and they tell that you still need a careful simplification to get the result. Okay, so I want to do it in a different way, and I'm going to use some classical techniques in point processes. One of them is the smoothing lemma. So the idea of the smoothing lemma is that if you have a stochastic integral, you want to compute its mean, and you can compute it in this way, actually in a simple way, by just replacing the jump term by the intensity, which is here lambda times ds. So that's the classical result in point processes and jump processes. But now what we have, as I mentioned earlier, we have something that depends not only on an x, but also on the terminal value of the Poisson process. In this case, this technique is no longer applicable, and you have to use this maker formula from the 60s, which is an extension. So if your integrand depends on the future in a sense, or at least it is not predictable, then you have to take care of this operator here, which is adding a jump at time s. Adding a jump anything because we only used ns minus the left limit. So if you add a jump at time s, the left limit is not much. That depends on the future. And adding a to ns plus 1 because it's a plus 1 operation, you add one jump. So that's the idea for the first moment, cover the previous result for the first moment. And what we can see is that it is much more streamlined. Okay, so you get the epsilon plus, you have the previous quantity which comes from the
Nicola, we are not hearing you.
And essentially, it means ns changes to 1 plus ns, 1 plus ns changes to 2 plus ns, and nt changes to 1 plus nt because one jump. Then the ULs, they are here. This is the formula I want to use. The formula I want to use is here.
Luis, we can do something or not?
No, I think the problem is with Nicola. Her connection
with respect to the Poisson process. So it's very similar to the previous one.
For instance, now it's
that we have this operator here, which is adding. Yes, yes.
For me, it's okay, the sound now.
Okay, thanks.
Okay. Oh, now it's good. And now you can hear me.
Now it's
so
okay.
I just continue of jumps now at times S1, SK. Okay, then I carry on. Yes, so going back to the, so before showing how it works, I will just recover a very classical setting, which is the classical setting of Poisson short noise processes. So the Poisson short noise process has jumps at the Poisson jump times, and at every Poisson jump time, you add a jump of size J1 and size J2 and so on. Okay, so in this case, if you apply the technique I described, you can claim that the moment of any order of the Poisson short noise process is given using the so-called Bell polynomials of those quantities here. Okay, and this is also connected to the previous combinatorial expression. How to prove this? Very quickly. Here, I write down my formula. I look at the addition of jumps here, and since inside here I have J, the jump size at time ns1, well, ns1 becomes 1 plus ns1 because I add one jump. And here nsl becomes 1 plus nsl. Okay, and the previous formula uses sums over partitions, and the sums over partitions, they really express the Bell polynomial. So we recover this classical result. Now we can move back to the, so I skipped this slide. That's my claim already. Now we can move to the growth collapse process. So I'm just here applying the previous formula to this anticipating Poisson stochastic integral, which is connected to the growth collapse processes. And you can check, it's not that complicated. You have the sum over partitions, and then anywhere you got ns, now it becomes L plus NSL, because up to time SL we add L jumps. And your NT here becomes K plus NT, because we add at most K jumps. So now what we have to do is simply to compute this expectation, and this can be done in classical ways. So then we get this expression. It looks complicated, I know, but it's not very difficult. The function we have here is linked to the moments of our random variable, and if the factors, the cutoffs, they are called cutoffs, are uniform, then this will be some form of beta function. Otherwise, it's the coefficient that you can see here. And no, so that looks very awful. So this is the formula we get in the case of uniform cutoffs. And I will move now to particular cases. Okay, so particular cases, this is now the formula which gives the moments of all orders. So previously we had the formula for the mean, a formula for the variance with strange coefficients, but now the coefficients are explicitly computed. And those numbers here, they really come from sums over partitions. And from there, we can also identify the long-range behavior of the moments. So there's a long-range behavior, actually, for this process. Okay, so now what can we do when we have moments? This is the formula for the third moment. I got it now. You can compute cumulants. And once you have cumulants, you can be interested in quantities such as skewness. I will add that here I'm plotting the curve, the analytic version, against the Monte Carlo simulation, just to make sure that I really recovered what I expect to obtain. I see that my time is almost up, so I will end now with a few more illustrations, so you can do the fourth cumulant. From the fourth cumulant, you can get to the kurtosis. And now, just to be more relaxing, I will just look at some pictures. So what can we do in terms of application? This is an application to neuroscience, where a short noise process is affecting synapses and is used as input. And very quickly, in the remaining time, I will look at some applications of cumulants and moments to skewness. So from all of this, using sum over partitions in this model of neuroscience based on a short noise process, you can now estimate the evolution over time of cumulants, but also of skewness and kurtosis. And you can now check the evolution over time of your distribution using techniques such as Edgeworth or Grand-Charley expansions, which are using cumulants and moments and skewness and kurtosis. And this is what we get here. So what we have here, the black line is a typical diffusion approximation, which is not really fitting the actual curve because, as we can see, there is skewness and kurtosis, which you can obtain if you compute moments and so on. So you get a better information, and this is the evolution over time with a fit based on skewness and kurtosis. So I consider that my time is up now. I want to remain on schedule. So thank you very much. That's the end of my talk.
Thank you very much, Nicolas, for the very interesting talk. Maybe you have time for one short question. If the question can be addressed by chat, okay. Wait some time. If someone can make some question, okay, the question can be written on chat. Okay, I don't see any question. Just to see here. No, there are not. Okay. There are not questions. No, okay. Okay, just to verify. Okay, there are no questions. Then, okay, in any case, you have where you now is time for the second speaker. Nicolas, thank you very much for your very interesting talk. Then you can pass to the next speaker. Thank you. Then, okay, now Our next speaker is Professor Benedetta Ferrario from the University of Pavia in Italy. Professor Ferrario has a wide research work on stochastic partial differential equations, namely on nonlinear hydrodynamic equations, has Navistox equations, Euler equations, and other related models. And today we'll speak about large time behavior of damped viscid fluids with stochastic forcing term. Please, you can start, Benedetta.
Thank you very much for introduction and for invitation. So now I think you can see, wait a moment. Is it fine for you?
It's perfect.
Okay.
Thank you.
So I want to tell you something about Euler equations. And in particular, we want to, this is the outline, to speak first of all of the Euler equations in the deterministic setting. So there is no forcing term. And when there is a no forcing term, there are a lot of conserved quantities. And then we will see how to use them, especially in the two-dimensional setting, which is easier. So because we can introduce a vortice formulation. What is a possible approach to the study of these equations, and why we introduce a stochastic forcing term and a damping term. So this is item number one. Then looking for log time behavior means to look first of all if there exists an invariant measure, and later on, second problem will be uniqueness of invariant measure and convergence, but today we focus on the existence. And the classical technique is the so-called Bogoliubov-Krylov technique for the existence of invariant measure. So if you work on stochastic PDEs, for sure you know this technique. If you do not, I will try to give you some suggestions. We have to revise this technique. Why? Because we will work in the space and infinity, you will see in a while why, which is not the Polish space, which is the basic assumption, first one, it's a requirement in the Bogoliubov-Krylov technique. And so in a sense, the aim of this talk is to tell you there is a classical technique which is not applicable in the usual setting to our setting for Euler. So we have to look for modifications and how to adjust what does not work in order to try to follow at least the line given by Bogoliubov-Krylov technique. And actually, at the end, we find that we can apply. So we found a result about existence of invariant measures. So let us start with Euler. Euler equations, they describe the motion of inviscid fluids. U is the velocity, is a vector, d-dimensional, let's say at the beginning, and p is a scalar. So the first equation is a nonlinear one, and it is a vector equation, so d scalar equations. And the second equation is the scalar one, so we have a d plus 1 equations and d plus 1 unknowns. Okay, that's fine. Maybe you are more familiar with Navistox equations, but it's not only because you are more familiar that I write down Navistox equation. Because, look, Navistox equations are the equation for model for viscous fluids. Nu positive is the so-called kinematic viscosity. And there is a big change, because if you take nu equal to 0, okay, you recover Euler equations. But actually, mathematically speaking, Navistox equations are non-linear parabolic equations, and Euler is a different matter, okay? So anyway, in both cases, you can look at individual solutions or statistical solutions. This is our focus today, statistical solutions. What does it mean? We want to provide a statistical description of a motion of fluids as it appears in turbulence theory. The K41 theory by Kolmogorov involves a lot of statistical means, and you need a measure to provide a statistical mean, okay? This is what we are looking for. You can do both for Euler and for Navistox, but the turbulence arises in the limit when the viscosity goes to 0. So it is very interesting to get results not only for Navistox, they are available, there are a lot of results in the literature, but also for Euler, which is more challenging. Of course, you have to pay attention to the boundary condition. Fernanda is an expert on this. Later on, we will work on Euler and Navistox equation with periodic boundary condition of a torus, which is the easiest case. We can do something with the Dirichlet boundary condition, but not in the general setting. That's enough. So let us come back to Euler. Deterministic without forcing term, there are a lot of constant of motions. For instance, energy in dimension 2 and 3. By this I mean that if you take this quantity, 1/2 integral of the square of the velocity, integral in the space variable, you take the derivative with respect to time. If the solution u, the velocity, is regular enough, you find that the derivative with respect to time is 0. And in dimension 2, this is true also for the entropy and also for other integrals. Look, energy and entropy are two quadratic quantities. And so people realized that by means of these conserved quantities, one can try to construct stationary measures. This is a crucial work by Oliveira and Cruzeiro. They constructed the so-called Gibbs measure on the entropy. It is easier to work with the entropy than with the energy. And since these are quadratic expressions, you find a Gaussian measure. It is a pretty interesting approach with some difficult technicalities, but it works also for Navistox when you add a stochastic forcing term. However, Navistox, in a sense, I told you before, is a bit easier. And actually, if you are not in the setting of Oliveira Cruzeiro, but you choose the spatial regularity of the noise in a general way, there are a lot of results about existence, uniqueness of invariant measure. I mean, I can't quote all the results because the list would be too long. But now, why do we add a stochastic forcing term to Euler? Because we would like to follow the same lines. So first, now we work in the two-dimensional setting. It is easier. If you introduce the new unknown C, which is the curl of U, so-called vorticity, C is a scalar because you are in two-dimensional setting, and curl actually is in the third direction, so only one component. Okay, it's a scalar. And the equation, the Euler equations written this way, the first line, has a nice property. I mean, it's like a transport equation, okay? And so it makes easy to get a lot of a priori estimates, which are usual to deal with such equations. But if you add a forcing, stochastic or deterministic, you destroy the conservation of what you had before, energy, entropy, and so on. However, if there is a damping, what I put the gamma, coefficient gamma, red one, in the left-hand side, one can expect that the balance is restored. And now the damping term is gamma, positive coefficient, times C. This is a similar approach to Navistox, what I told you before. But look, mathematically, the damping is a zero-order damping in Euler. In Navistox, it's like Laplacian, which regularizes a lot. I mean, it's really a different mathematical problem. But the idea behind this approach is the same, exactly the same. Mathematically, it's different. So from now on, we deal with system number 1, gamma is so-called the sticky viscosity. And if you look for motivation for such an equation, you find the book by Galabotti, one of the books by Galabotti. And there are known results about global existence, uniqueness. I only point out uniqueness. You need the initial vorticity to be in L infinity. And this is our difficulty. And of course, you can choose a spatial domain, which is the torus, or a smooth boundary domain. And we take W, which is time, white noise, and very regular in space. The regularity in space is not a problem. Take as regular as you need, okay? Stationary solutions have been proved by Bessai, which is a co-author about the result on invariant measures. And look, they work, they live in space LP, 1P is finite, which is a separable Banach space. So it's something different from an infinity. However, we want to speak of invariant measures. The two concepts are not equivalent. Stationary solution is a stationary process solving the Euler equation. An invariant measure is something which is related to Markov semigroup PT. So we have to define, first of all, a Markov semigroup. So Bogoliubov-Cleo technique is a classical technique to get existence of invariant measures. We are working on uniqueness, but it's not yet finished. So I will speak about existence today. Here is the Bogoliubov-Cleo technique. You find it, for instance, in one of the books by Daprat and Zabchik. First, define a Markov semigroup. It acts on observables, phi. And as soon as you check two properties, a Feller property, which means that PT maps continuous functions into continuous functions and bounded. The continuity is the crucial point. And if this sequence of measures, which is a time average of the law starting from 0, is tight in the space X, you find existence as soon as X is separable by X space. Look. We have to work with an infinity because there we have uniqueness and you can define the Markov semigroup, but an infinity is not separable. Actually, in an infinity, you can put different topologies. The strong one, you know very well. The weak star topology, for sure, you know. And in between, there is the so-called bounded weak star topology. I only stress two properties. No, this one is crucial. An infinity is not separable when we consider the strong topology. However, if you choose a weak topology, of course, it's not metrizable. And so, for sure, whatever is your choice, an infinity is never a Polish space. So that's a trouble. That's the origin of our problems. There are three properties about these weak topologies. Number 3, they are really different. The weakest is the weak star. Number 4 means that continuity with respect to the bounded weak star topology coincide with sequential continuity with respect to the weak star topology, which is crucial because in a metric space, sequential continuity coincide, but not with the weak topologies. However, the two weak topologies have the same Borelian subsets, which are a poorer sigma field with respect to the Borelian subset for the strong topology. Okay, and so what we have to do is we have to choose which one, and we choose the weak topology because if you look for tightness, you remember in Bogoliubov-Cleo, okay, if you have a weak topology, it is easier to prove compactness, and tightness is related to compactness, okay? Actually, the idea comes from a paper by Maslowski and Seidler. More than 20 years ago, they wrote a paper, very interesting one, but applications came later on. This is one of the applications of Maslowski and Seidler technique, revisited again because they worked in a separable Hilbert space, but the idea comes from them. Okay, take our equation, look for some good bounds, they are written here. You find that uniformly in time, when you start from 0, the solution is such that with high probability, it is concentrated in a ball of suitable radius. This is tightness for also, not only for the law at time t, but also for the time average. This is tightness because the balls of an infinity are compact with respect to the weak star topology. Okay, that's fine. What about transition semigroup? First of all, we need some continuity, and we have the sequential continuity I told you before. Sequential continuity is a crucial tool, which is pretty easy to prove. I mean, it was in a sense already available in the literature. And if you combine, first line, if you combine all these compositions, you start from initial data, and then you take the solution time t, and then you take you apply phi and the mean value, so you construct the so-called operator PT, you find that it is not failure, but it is failure with respect to the new topologies we have introduced. Okay, yeah, we are happy. And now we have to prove that actually PT is a Markov semigroup. So the Markov property, which is number 8, has to be proven. And this is a long way. So we needed a few pages in the paper. It's not short because the usual proof of Markov property is based on the separability, and I mean, yeah, it's a problem, but we found a proof for Markov property. And when you find this one, and when you find the Markov property, you get mathematical, you take mathematical expectation and you find the same group, the same group property. Which means, if we sum up, we have been able to construct a Markov semigroup in the space L infinity with the bounded with star topology. We proved that it is Feller when you have chosen such a topology, and you proved that we have tightness. And so, follow Bogoliubov-Krylov. Just one detail is missing. We have to pass from tightness to extracting a subsequence which converges. You can't use Prokhorov. We are not in a metric space. There is another result in the literature given by Jakubowski working in non-metric spaces, and we are done. We have to satisfy some assumption, but it's fine. And then here, if you know Bogoliubov-Krylov technique, I summarize here how it works. You take the action of PTphi with respect to integral with respect to the measure mu n, you extract a subsequence, and you divide in 3 contributions. The second and the third will go to 0, and the first one is what you keep in the limit, and which means finally you are able in the limit to prove this result, which is nothing but the definition of invariant measure. So this is, we sum up the result. Take gamma, which is positive, any positive gamma, and there exists at least one invariant measure, mu, for the stochastic damped Euler equations. Okay, that's all. Thank you very much.
Thank you, Benedita. We have 3 minutes for questions. There are some questions. Okay, meanwhile, I have maybe one question. For this damped model, I don't know, there are invariant, for the deterministic model, I ask, okay? There are invariant measures in this line of Alba Velho Cruzeiro? Or not? It is proved in literature. There are some let's say invariant measures, or maybe quasi-invariant measures is possible to prove.
Formally, you can write down the Gibbs measure of the entropy, but the solution of Euler already for the let us think of Navistox. We make the parallel with Navistox.
Yes.
Already the solutions on Navistox are difficult to analyze because the support of invariant measure is a distributional space. So these are not classical solutions. And for such a damped Euler, to find a result about existence of such solutions is very difficult because you see, Navistox, usually you work in the space L2 for the velocity, and here for the damped Euler, you work in the space L infinity for vorticity, which means the velocity is W1 and infinity. You are far away from the classical solutions. For Navistox, there is you pass from, let's say, H0, L2, to H minus epsilon. So it's a small gap. But for Euler, is such a large gap in the regularity from the classical solutions, the solution you would find with this method, that it's hard to find the result of existence. It's really hard. So in principle, you can try, but for Galerkin, it works in the limit, nothing.
Okay, okay.
Too difficult. Maybe you can try.
Okay, okay, okay. Thank you. Okay, perfect. Let me see if there are some questions here in chat. I don't see more questions. Just wait some minute. Okay, okay. In any case, we have okay. Okay, now it's time for next speaker. Okay, then okay. Thank you very much, Benedita, for your very nice talk. Then we can pass to the next speaker. The next speaker is Professor Ana Bela Cruzeiro from IST, University of Lisbon. Professor Cruzeiro has an extensive research work, okay, let's say in several different topics. Has a Malevin calculus, infinite dimensional analysis, okay, geometry on path space, and on a stochastic approach to fluid dynamics. Then, and today, okay, Professor Cruzeiro will speak on stochastic variational principles for Navistox equations in bounded domains. Please take the screen.
So thank you, Fernanda, for the introduction and for the invitation to be here. It's a pleasure. So let me try to share the screen. So I suppose you are seeing a file, right?
Yeah, it's perfect.
Okay. So I'm going to explain a little bit generally how a subject where I work for many years now, time passes, which are stochastic variational principles in, well, more generally in hydrodynamics, but I'm focusing here in Navistox equation. And well, the recent part, I'm going to start from things which are already quite old, and then explain, this is the more recent part, explain what we can do when we have bounded domains and in particular some boundary and how to deal with problems, how to deal with the boundary. So for those who are not experts in hydrodynamics, let me start from the beginning, which is the inspiration of all the stochastic, all the variational approaches to this kind of equations, which is the following. So consider the Euler equation, so which is, I mean, Benedetto has already spoken about it, and it's here. So there's the equation for the velocity of a flow of a fluid which has no viscosity at all, and which is incompressible. So the equation is a first order PDE. P is the pressure, U represents the velocity, and the incompressibility condition is divergence of U equals to 0. Okay, so this is typically people in PDE work with this equation when they talk about the Euler problem, but we can also look at what is called the Lagrangian approach to hydrodynamics, which is instead of looking at the velocity, you look at the position actually. So what do you do? You integrate, you consider this G here. Maybe I have a pointer, but I'm not very good with the pointer. So let's, I hope that you can see what I'm talking about without the pointer. Anyway, so this G here, which is in the second line, is the position corresponding to the velocity, which is also called the Lagrangian flow associated to the Euler equation. So it describes the position. Of course, morally, this is the same study, but this is just morally because in generally one doesn't have enough regularity to go from one to another. So U sometimes is not regular enough to define a G, and so it's not totally equivalent mathematically speaking, but intuitively it's, well, just you study the velocity or you study the position, and G will always be the position for me. Okay, so G are flows representing the position or Lagrangian flows. And then in 1966, Vladimir Arnold published a paper where he made the study of this equation based on the following sort of remark. It's not difficult but deep remark, is that actually these G's are geodesics on some space. So it's a big space, it's the space of all flows, of all these paths which are measure preserving, so volume preserving because of the incompressibility. But this, of course, is a very big space. So when you say geodesic, I should have put a comma here, because what you mean by geodesic, you have to have some geometry to define a geodesic. Anyway, one possibility to describe a geodesic is that it minimizes, or at least it's critical to the length, the square of the length. And so that's what it is. There we have a variational principle. These Lagrangian Euler flows are critical to the action functional Sg, which is written here. You can see it very easily. You just derive the Euler-Lagrange equations and you see that you obtain the Euler equation. It's not a difficult computation, but it is a very important remark. So now what I have been working again, as I said, for years now, is well, this works for Euler equations and works for many other equations which are conservative, in fact. And geometric mechanics has a very general framework. So you see these G's and their composition will form also a group. So we have to have a manifold around here, which is infinite dimensional of the diffeomorphism, but it's also a group because you can compose these flows. So and geometric mechanics has a whole machinery to deal with this kind of things. Of course, this is infinite dimensional, but they can also deal with this. And for them, this is just a particular case of a general framework where they obtain also other equations. But always when there is conservation. So the system is always conserved. Now, you may ask, some of you may ask, what is the probability here? Because I didn't say a word of probability, but it will come. I have here a problem. Oh, okay. There was something that popped up in my screen. Okay, so in terms of what I want to study, I would like to study this kind of approaches, but not for conservative systems, but for dissipative systems. So when, say, the energy is dissipated. And in this case, we have the main equation, and the main example that I want to study is, of course, Navistox, where you do have dissipation. So you have this extra term related to viscosity. Mu is the viscosity. And the question is, can I get this as a solution of variational principle? Well, not exactly as before, but then probability comes along. I can, yes, look at this, the corresponding Lagrangian flows as a sort of geodesics in the same kind of spaces as the Euler flow, but giving some stochasticity. So I'm interested in the deterministic Navier-Stokes for the velocity, and the price to pay is that the Lagrangian flows, so the position will not be a deterministic path, they will be random paths. So, okay. So what I'm going to do is that I replace the equation for G there by a stochastic differential equation where the drift is U, but then there is a Brownian motion, and the variational principle by a corresponding variational principle that we'll see later on. Also, just a remark that we don't consider external forces, but we can. Well, okay, it's just a remark. I wrote it in a general manifold, but for those who don't like manifolds, just think as this metric G, bold G as the identity, and these gammas appearing here, which are the Christoffel symbols, you just don't think of them, that's zero, and then you have a normal Brownian motion, okay? So I wrote it in general, but you can just forget about the gammas, about the sigmas, because that will be given by the metric, which is the flat metric. Also, this is the identity. So if you in the general manifold, you write the Brownian motion like this, but if with a drift U, but otherwise you just would have dg, a stochastic differential equation, which is dw, some Brownian motion, plus the drift U. So these G flows, again, will correspond to a description of a stochastic position of the particles, but instead of being just defined by the equation, the ordinary differential equation with velocity U, they have a random part. If we compare with the last talk of Benedetta, I stress that we are not talking about SPDEs here. We can talk about SPDEs, we do. We also have variational principles for stochastic Navistox equation, but that's not what I'm talking here. I'm talking about the U satisfying the deterministic Navistox equation, and the G satisfying SDE, as just a stochastic differential equation. So here is the generator. So in the flat case, it's just Laplacian plus the first order term corresponding to the drift U. Then we define D, which actually coincides again with the drift, which is a sort of generalized derivative. So as you know, given that the G's are random, are driven by Brownian motion, they are not differentiable in time. So we have to put here a conditional expectation to define some sort of derivative in time. And the action function, which replaces the one that I showed you for the Euler equation, will be, so the difference is that instead of a usual derivative in time, you have the drift, so this generalized derivative, and we have an extra expectation before the integral. But other than that, which is already a lot, of course, but other than that, we have exactly the same structure. We have an action functional that we want sort of minimize or make critical for computed on the position of the particles associated to the velocity U, which are now random. So how do you make the variations? Well, you derivate this in particular this functional. You derivate in directions given by velocity by vector fields V with divergence 0. By the way, I didn't write that the divergence V equals to 0, but it should be. We are working in the space of diffeomorphism. Well, don't think too much about the regularity, the space of flows which are conservative, so that keep the measure, the volume invariant. Okay, and the general theorem that we can get from here, and again, you can think of it in the flat case, not necessarily in a manifold, is that the U is well, U a priori is a divergence-free vector field, and G will be the Brownian the flow, the stochastic flow, which has the drift U and a Brownian motion. And then this process that I called that I write GU, it always defines the position. It's always called U. Is critical for this energy if and only if the vector field U satisfies Navier-Stokes equation. So here on a manifold, you get the Ramage the Laplacian, but if you are in a flat case, it's just usual Laplacian. Okay, so these things are the basis that where we started from, working at these kind of things a long time ago, in particular with Fernanda, and now the point is that what I'm going to explain now is what do we do if we have. So for the moment, the manifold didn't have a boundary. So the boundary complicates things, and it can be a manifold, well, a nice, regular, connected, but without a boundary. because we work, because the definition is an infinite dimensional space, is the group or the space of diffeomorphisms which keep the measure invariant, but everything is defined in a manifold, and the fact that the divergence is 0 is included in the definition of this manifold or this big space. So it's incorporated there. So you have a space where you already have the condition that it's incompressible. So the point is that if you want to work in these kind of spaces with boundary, it's kind of difficult to construct flows which keep the measure invariant, and because of the structure of the boundary. So one idea that what I'm going to explain here is to replace the construction by a finite dimensional one. So we define some variational principle, also stochastic, for the Navistox equation on the bounded domain with a boundary, but not on an infinite dimensional space, just on a finite dimensional space. And so how do we get incompressibility? So if it's not incorporated in space, how do we get it? Well, we get it as a Lagrange multiplier. So we transform the problem into a finite dimensional one in the same spirit and with an extra Lagrange multiplier. So this is essentially what I was talking. It's just written here. So now I'm on a domain in RD. By the way, the dimension doesn't in this structure. The dimension doesn't cause a problem. It can be in any dimension as long as things are defined. But it's okay. So you consider here now domain O with a boundary. And instead of just considering a Brownian motion with a drift U, you consider a Brownian motion with a drift U plus N is the normal to the boundary. And you consider plus this excess term where L is the local time associated with the process G, which represents, as you probably know, since we are in a probability session, it represents the it represents the amount of time spent by the G, by the process in the neighborhood of points at the boundary. We have the same definition of the generalized derivative. And we have an action function which is now defined as the term which was there before, so the term of the generalized derivative that as I'm indicating, it generalized the usual time derivative of the position. And then we have an extra term here which is the integral of the P, of the pressure. And multiply by determinant the gradient of G minus 1. So this term is a Lagrange multiplier, and we are going to force the solutions to have determinant 1, which is the same as being incompressible. The variations are simpler here because you don't have to keep the structure. I mean, the fact that, as I said before, the fact that we have incompressibility will be given by the Lagrange multiplier. It's not in the space. So the variations are simpler. You can just take variations as, before we had to keep the group structure when we made the variations. But here, no, we just made variation, we just defined variations by summing additive variations, so by shifts. So both of the G, the position of the P. So here we have an action which is defined on G's, solutions of stochastic differential equations with some drifts, and also P. And we are going to ask what are the G, that's since we have the Brownian motion fixed, what are the G means what is the drift, and what is the P that are make critical this action function. So the variations are smooth, deterministic, and the theorem is the following: a diffusion of this form. So you have again the drift plus the extra term that describes the behavior at the boundary. So this diffusion and a function P are critical for the action function if and only if we have Navistox equation with this orthogonal condition at the boundary, which has a name in hydrodynamics. Fernanda, you probably know the name. For people working with fluids, this is called, well, you see what it means, right? It's something with, well, I don't remember what they call it, but anyway, this is the condition at the boundary. Well, it's Neumann if you use the terminology of PDE people, but hydrodynamic people have a more intuitive name, which I don't remember. But you see intuitively what it say. The derivative will also always perpendicular to the normal, so it doesn't sleep. It's non-sleep, maybe. I don't know. I don't remember the name. Okay. So you may ask, before in the Arnold and so on approach in infinite dimensional space, I didn't speak about the P, the pressure. So the P is given a posteriori in the sense that the P is related, it's the dual variable to the fact to the condition, it's the dual to the condition that divergence is zero. So the P is given afterwards somehow. Here it's given at the same time. So we have the variational principle gives you a U, a velocity, and a P. Okay, now so maybe I have a little time to go into the proof. So you have, let's see, the action function has a term which is as before, so it's the sort of kinetical energy in this generalized sense. So it's the square of the velocity in time plus the other term. So I call it S1 and S2 here. S1 is the stochastic, is the kinetic energy, and S2 is the one with the pressure and the Lagrange multiplier condition that I want to have. So I have to make variations, again, given as here by shifts of both terms. So let's start from the second one, because the second one is not really very much stochastic. All the computations are deterministic, are even sort of algebraic. So first you make variation in the P. Since the variation in the P is arbitrary, any phi, this immediately implies that the determinant of gradient is equal to 1, so it's incompressible. So you have, as a Lagrange multiplier, you get immediately that the determinant of the gradient is 1. Then you have to do, okay, so this is the first line of this slide, because you have any phi when you variate the P, you immediately deduce that the flow is incompressible. Then you have to make the other variations, the other terms when you compute the variations, and you have here, well, the second one also disappears because you know from the first one that this is incompressible. So the second one disappears, and then you have to derivate this determinant of the gradient. And this is purely algebraic. So you have, okay, there's a lot of indices here, so it's not very practical to follow. But if you derivate this product, well, it is just derivating a product, and at a certain point, you have a derivate in the last term of the gradient of G minus 1, which turns out to be 0. You can compute this. It's really linear algebra. Well, plus some derivation, but I mean, the computations are very easy because we have this determinant of the gradient G equals 1. You can deduce that this is 0. And then you derivate the determinant in space, and you know that the derivation of the determinant is the trace. And again, this will give you 0 because the determinant of the gradient G equals 1. And therefore, this term will give you at the end. Of course, I mean, it's not easy to follow like this, but you may believe me, and you may look at the paper for the details, that this term, the second term with the pressure, will give you, when you variate in any direction, you give you minus the expectation of gradient of P scalar H, and the H is any variation. Concerning the first one, well, then you have to use the Ito calculus because you are working with this sort of generalized time derivative or drift. So you have to use the fact that the d, little d differential, Ito differential of the product is the product of differential plus an extra term. And the extra term, the extra term is very nice because it will compensate on the other with another term, and at the end you get also a Laplacian. You get a Laplacian coming from this extra term, and you get this variation for the S1. So it's double the second derivative of G minus, there is an H missing here in the first term, plus this extra term coming from Ito contraction. And since we have any variation, at the end, you will get the Navistox equation plus, and don't forget that the stochastic flows have this L of T, this local time incorporated, and give you at the end the equation with gradient of U orthogonal to the normal at the boundary at each time. Okay, so again, and the computations and the proof is not difficult. Again, one part is pure, almost algebra, and the other part, well, it's stochastic calculus. Okay, so we have a variational principle. In the case we have a bounded domain with boundaries. I wanted to just very rapidly. I still have time, but maybe I'm not going to use all the time because now I'm going to be not give very details. You have because you have a variational principle, so you can think about things like conserved quantities, or you can think about relating it to kind of Noether theorem. So we do have conserved quantities. If you consider transformations of this sort, so you shift the trajectories into directions eta. Again, we did it smooth and so on. Then you have this Lagrangian that was the term that we integrate in the action function, as I wrote before. And it is invariant under these transformations associated with the eta. You can prove that this is true if there exists a function such that this Lagrangian, derivating of Lagrangian is equal to the G. Oh, no, you can prove. You define it to be invariant if the derivation of the Lagrangian along these transformations is dT for example, it can be 0, but it can be more general than that. And we have a sort of Noether theorem, well, not exactly, but in the same spirit, is that this Lagrangian is invariant under these transformations that I wrote before. If and only if we have this identity. not if and only if. So it implies that we have this identity, which is an identity that you can check, right? You can then try to find etas that verify this equation. L is the, again, is the generator of the process. And well, it's easier said than done, because well, I tried to have some, to get some examples, and the examples I got were not so difficult to get. I mean, I got some quite simple examples, but anyway, you get some sort of characterizations of the invariance of the transformations that keep the invariant the structure of the Lagrangian, so like in the spirit of Noether's theorem. And then we also have, now I'm going to make comments, we also can deal with other equations. So I focused here only in the Navistox equation, but you can get a lot of examples, which are, for example, Kamasa-Holmes or MHD, magneto-electrodynamic equations, well, with an extra work. But anyway, there are many examples that we can treat by stochastic variational principles. And the questions that you can ask once this is established are the following in particular. Maybe there are others, but certainly there are others. But what about, questions are, what about how this probabilistic approach to the Navier-Stokes equation, and again, other equations, helps in finding solutions, okay? So how do you prove that this critical path exists? So a variational principle characterizes them, but you would like to have more than that. You would like to have a way of proving existence. So, and this is a subject that, this is a general subject that I've been involved in for quite a long time too, because this is not easy. Well, one could not expect it to be easy. I mean, if it would be easy, that would mean that you would prove existence of Navier-Stokes solution easily, which is not reasonable to expect. But how to approach this problem in a probabilistic way. And so for those we are interested, well, I may give some extra reference if people contact me, but anyway, direct methods, as far as I know, don't work at all. At least I never could use them. So there are three kinds of methods essentially that we could use and prove some things, not a general solution, of course, and that not in not a full approach, but in certain cases and under certain restrictions. The three methods we used were: one, entropy minimization problem. So that's minimizing the energy, like I defined here in the stochastic case, can actually be shown to be equivalent to minimizing some entropy. And so we try to develop to use and develop the entropy methods to prove something. We proved something, not everything. The other idea was to use forward-backward stochastic differential equations, because you see there is a position and a velocity. And if you write the position satisfies the stochastic differential equation, and if you write the velocity on the trajectories, it satisfies also another stochastic differential equation. And you can look at it backwards, and the system is a second order system. Is a forward-backward STE, and there are many people working on that. So this was one approach, but again, it was not easy because the space behind was infinite dimensional, and so we could do something in 2 dimensions. And well, then the dimension here is very, very important. And the other possibility is to get what is called generalized solutions that Brenier developed for those who are interested in optimal transport. Brenier gave some kind of generalized solution associated to Euler, and then we can sort of adapt or generalize this approach also to Navistox and to stochastic paths. So this is again another approach, but I'm not going to, just to say that there are still many things that we can do in this approach. I wrote here the other, for example, the other equation which come as a whole, but I think I'm not. And also all these are particular cases of, so when you work in the group of diffeomorphisms, you work in a group because again, by composition, it's a group. And then it's a particular case of what is called the Euler-Poincaré principle in geometric mechanics, and you can do this stochastic Euler-Poincaré principle. So this is also a subject that I am involved in. So here are some references. I think I'm going to end with these references. So starting from the beginning, so starting from the end of this list. So the first paper that we wrote about stochastic variational principles for Navier-Stokes was with Fernanda in 2007, and then in the case of manifolds with Marc Arnaudon some time later, and this paper by Xin Shen, Marc Arnaudon, and myself, stochastic Euler-Poincaré reduction, gives a general framework in the generally group. And then the first two papers that I refer here, well, the very first is the one that I mainly talk today, which is the case, which is when you give the variational principle using Lagrange multipliers for the pressure. And then there is another one where I make a review of all this, so in case you are interested. The second one. So I think we still have some time, but I think I'm going to stop here. And thank you for the attention.
Thank you very much, Annabella, for your very nice talk. Okay, now we have some time for questions. Okay, please, if someone want to do some question, can write the question on chat, please. It's better to wait some time because this takes time to write.
Yes, I had this experience. I don't know in what talk I was trying to write a question, but I couldn't write it quickly, so then I walked.
Yeah. It's better because
it's definitely not the same as having a conference with real people around.
Yes, it's not.
No. Well, we can get used to it, but it's not the same.
Yeah, it's not. But
so after a while, I said, no, I don't ask questions in this conference. If I have a question, I send an email to the speaker afterwards. It's kind of calm. Oh, but there is something. No.
Yeah.
I don't see.
Annabella, please.
Wait.
Yeah, it's okay. We are hearing you.
Wait. Is the stochastic Lagrangian flow? Okay, so the question is, I'm reading it. Is the stochastic Lagrangian flow related to the Lagrangian flow in de Bernoulli theory? Well, if I remember correctly, if you are talking about the de Bernoulli measure, then this is a measure for the velocity. So my Lagrangian flows are positions, and de Bernoulli is for the velocity, and he defines some measure. And when I wrote here that we did study some generalized solutions in Brenier type, we have some, it's kind of statistical solution related to this. So we have some not, the Lagrangian paths are not really diffusion, but we have some statistical solutions. So we have some extra probability here. And then the velocity are flows and measures that are indeed the Bernoulli's type. But that's a little bit different than what I exposed here. I don't know if I answered enough your question, but I can send you an email if you want. We can continue the conversation if you want by email or something.
Yeah. Okay. Okay. I don't see questions. Okay. Maybe I can ask a question. When you write this variational principle for bounded domains, okay, you recover the Navistox. You write the action functional, and you recover the Navistox equations. Yeah, right. With this special boundary condition. My question is the following: first, you recover also the initial condition, and in addition, if you can consider this deterministic problem that you recovered, okay, directly from the variational principle, this problem is well posed from the deterministic point of view, or not?
You mean the PDE?
I mean the PDE with the initial condition you get and with the boundary condition you get. Let's say
well, in some cases it's opposite, but then I don't get this kind of results. I mean, these are results which can be imported from PDE people. You see?
Yeah.
I don't get any kind of. Again, this is the problem. How do you use this characterization to show that that there exist solutions? Well,
but you recover for instance, for the initial condition, you recover the initial condition because you have your variations are 0 in the initial point and 0 at final point. You are able to recover the initial condition?
They are 0 at the initial point and the final point for the position.
Yeah, not for the velocity?
No, this implies that you start from, so this kind of variations imply that you start from a fixed point and you end at a fixed point.
Mm-hmm.
But I'm talking about the position, not the velocity.
Okay. There are no restrictions on the velocity. Yeah?
No.
Okay, nice. And the other thing is that you make a variation of the velocity and on the pressure, but in my idea is that when you make a variation of the velocity, automatically this implies some kind of variation of the pressure or not? Because I think
no, they are independent. They are absolutely independent. So, I mean, they are treated as independent variables. And they make a variation of one which has nothing to do with the variation of the other. And at the end, you have that this is critical if and only if they mix together. Well, but they mix together because of the definition of the action, not, they are independent variables.
Yeah. Okay.
So, I mean, you cannot, I don't think, I'm just talking, but now I'm not, I don't know if I'm saying something serious, but I don't think you can see the variations as, okay. The equation, of course, the pressure is related to the velocity. If you move the pressure, you have another velocity, and I suppose the other way around. But in the variation, in the principle, you don't see that. You make variation which don't influence each other.
Okay.
Because they are independent variables.
Okay. Then okay, just to take a look if there are some
I
questions?
don't see any. I suppose that in the same place where I had the question by Kiao Huang, I would have another, and I don't see any other.
Okay, then.
But again,
okay.
if you feel free to send me emails when you want.
Yeah, of course, you can send. All people can send you an email and ask properly the question with time and so on. Okay, I think it is.
Wait, there are things happening. No, that's. But I think there is another question.
There are another question you can see?
No, maybe not. Maybe it's the same. Sorry. Nothing. I didn't say anything.
Okay. So, thank you very much for your very interesting talk.
Thank you.
And
thank you for being there and for the invitation.
Okay. Now I think it's time to you can finish here. And okay, I'm very grateful to all of you for your availability to share with us your very interesting research work. I thank you very much for coming. And okay, I hope you can you met in near future in person. We hope you can meet in person. Okay, not by this way. Is much better. Okay, and I don't know, Luis. Maybe you can finish here.
Yeah, it's okay.
Okay,
For me, it's okay. Thank you very much for everything.
And I can say to you thank you very much again, and goodbye.
Bye.
Okay. See you. Bye.
See you. Bye. Thanks.